Hello, everyone. So today we are going to finally have a chance to begin applying what we've learned about symmetry and taking it from the molecular level and actually really playing around with what we know about orbitals. So this is uh, going to be this major idea that I can go ahead and start by, say, assigning a molecule like SO2 to a certain point group. In this case, C2V. But it turns out that just because my molecule is C2V symmetry and obeys certain matrix operations, it doesn't mean that all of the individual atomic orbitals that I use to build up its electron density will respond the exact same way. So what we're going to be doing is specifically looking at SO2 and a subset of its p orbitals, which will really give us a good general picture of how orbitals behave under symmetry. So the ones we're specifically going to be looking at is the p, x, y, and z orbitals on the sulfur atom, and the pz orbitals on the two oxygen atoms, which I'm going to now refer to as Pa and Pb. So the entire molecule is going to obey C2V symmetry, which means it is symmetric or yields its own image if I apply one of four symmetry elements: the identity matrix, a twofold rotation or a 180-degree rotation about the sulfur, a sigma V axis, which is a mirror plane bisecting the molecule, and a sigma V prime axis, which is another mirror plane cutting through the plane of the molecule. So what we're going to be trying to do is get a better understanding about the behavior of the atomic orbitals and how they interact and form molecular orbitals by seeing how they interact with our basic symmetry operations. And this is something we'll slowly build up over several lectures, but we can start to get a good appreciation just by looking at these base atomic orbitals. So in order to do that, first we're going to actually have to apply each of my matrix operations to each of these orbitals individually. So feel free to try and tag along by using our coordinate image of the p orbitals. So in order to do this, we're going to build up a matrix form, which I'm going to demonstrate as a table. And I'm going to give a value of 1 if my orbital turns into a new orbital. So if x becomes px becomes pz, I give that matrix element a value of 1. If it becomes that new orbital but switches direction, so positive becomes negative and negative becomes positive, this gets a value of -1. And if px has nothing whatsoever to do with py, that gets a value of 0. Turns out we're going to have a whole bunch of 0 elements. So we can either demonstrate this as a matrix, or I'm trying to do it in a more familiar table form, which should convey all the same information. So for this, we're going to have to apply all 4 of our operators. So let's start with an easy one. What about the identity operator? So this is going to have its own matrix representation, which we're going to give the name DE. And more or less what happens is I give the element of 1 if the orbital is conserved in its original place, which, because it's the identity matrix, nobody moves, nobody changes direction, because I did nothing. So px gets an element of 1, py, pz, pa, and pb. So all of my diagonal elements get a value of 1. Everybody else gets a value of 0 because px has nothing to do with the other 4 orbitals if I do nothing. And this is the major idea of a matrix representation of an operator. So it's fairly useful because you can imagine if you're playing around with matrices, I may have another matrix that represents some behavior of these orbitals, and then I say I do nothing to the orbitals and I get the same value back. Gotta love doing nothing sometimes. But it also illustrates the general idea of working with this matrix form. However, it won't stay this easy because it turns out I've got 3 more operators I need to apply. So let's go ahead and build up the next one, which is going to be our C2 rotation. So this is a 180-degree rotation about our principal axis, which we define as the z direction. So no matter the system you're working with, if there is a principal axis of rotation, that will tend to be our z direction. So in this case, my z direction points up into the plane, and we can go ahead and describe how each of these orbitals move with their own representative matrix, d, c2, or the representation of c2. So in this case, if I do a 180-degree rotation about this axis, px will stay put, but it will flip directions. Positives become negatives, and negatives become positives. So that gets a value of -1. Py also remains py, but again, flips direction, +1, -1, so it gets a -1 value. Pz, however, spins around like a ballerina and doesn't move anywhere, so it gets a value of 1. Now, unfortunately, we have our misbehaviors who are far out from the axis of rotation. Pa is going to become Pb, because this atom will rotate into the position of atom B, but when it does so, the positive becomes negative, and the negative becomes positive. So it gets a value of -1, and Pb also becomes Pa, but again, flipping direction. So these two flip direction, so they flip positions, and they flip signs. So we get -1s on these off-diagonal elements. All right, so let's go ahead and work on to our next operations, which are going to be our mirror planes. So our next up mirror plane is the sigma v, which we're defining as bisecting the molecule. So this is our px and pz plane. One of the things you should note when you're looking at point groups, as the one presented in your ones are presented in your equation sheet that I provided on the first day, they almost always define which plane is defined, XYZ coordinate plane is defined by a given mirror plane. In this case, again, we're bisecting the XZ plane, and so we can generate its own representative matrix. So in this case, because PX and PZ are along the mirror plane, neither of them will move either positions or directions. The PY will be reflected across the mirror plane and change signs. So it gets a -1 value. Now, unfortunately, atoms A and B misbehave, so they will flip positions but maintain signs. So again, now PA becomes PB and PB becomes PA, but now no negative signs are associated with this. So this then gives us our final matrix operation, which is going to be our second mirror plane. So this is the YZ plane. So this is the one that cuts along the plane of the molecule. So in this case, its representative matrix is going to have X flipping direction, so positive becomes negative, negative becomes positive, so it gets a -1. Y and Z maintaining in the plane will not move, so they get values of 1. And I apologize, this should be a -1 sign, but PA and PB will both flip signs but retain position. So for once, they actually stay put along diagonal, even if they change sign. So when we put this all together, we represented all of the possible movements that can happen as I use all 4 of my symmetry operations, but it took me 4 5x5 matrices to do so. And let's be honest, that's a whole lot of work. So we might want a slightly easier and more concise way of representing how each of these orbitals will transform or move if I perform a symmetry operation. So in order to do this, we can make use of a rather nice feature of how each of these matrices were formed. And that's that they all were part of what's called a block diagonal matrix. So this is where all of the elements either have values on the diagonal or near the diagonal. And we can do this as we can use this to make a very simplified description of how the systems behave. So we're going to be doing this by breaking our system down into 2 parts. So As we've seen before when working with molecular orbitals, diagonal matrices are very nice to describe. So we'll first start by looking at our px, y, and z orbitals and describe them. And then we'll go ahead and talk a little bit about how the pa and pb orbitals interchange and intermix. So starting with our x, y, and z orbitals on the sulfur atom, it turns out that when I have a form like this, I can describe how each of these matrix elements is affected by a symmetry operator using a single number. And this ends up telling me that all three of these belong to an irreducible representation, which you're also often going to hear me describe as an irrep of the C2V symmetry group. So where this name essentially originates from is the idea that I can't simplify their description or their representations any further. They behave as simply as possible as it is for a element of this C2V point group to behave. And so what we can do is describe each of these irreps in a matrix form, or again, in a table that describes exactly how each one of them transforms under a symmetry operation. Because remember, each of them only had a single value along the diagonal, because each of these orbitals transformed into itself just either with the same or a different direction. So because of this, we will describe each one of these using an irrep, which is given a gamma superscript notation. And each one of them behaves slightly differently under each of the symmetry operations. So it turns out I have three different possible irreducible representations, which I'm going to label 1, 2, and 3. So px, which is my first irreducible representation, doesn't move under the identity matrix, flips sign under the C2 under 180-degree rotation, doesn't change sign at all when I do a mirror image about the sigma v mirror plane, and does flip sign if I do a mirror image across the sigma v prime mirror plane. So again, with these four numbers, I tell you exactly how it behaves if it's moved according to any of these symmetry elements, which is important because each of these symmetry elements can describe a certain type of perturbation that the molecule or orbital can experience. So then we can do the same thing for my py orbital, which will maintain sign under the identity, as always, and it flips sign under a 180-degree rotation or a reflection across the sigma v axis, giving -1 values for each, and retains the same sign when it's reflected across the mirror plane in the plane of the molecule, thus a value of 1. Now our pz orbital is nice and special because since it's pointed along the principal axis, it actually doesn't move if I apply any of the four symmetry operations. So this irreducible representation is actually a very special case. It's essentially my identity operation. It's my fully symmetric operation. So if I have an orbital that behaves the same way as the entire molecule, it's going to have this irreducible representation, which is going to become very important later on. However, we do run into a problem because while each of these three orbitals are wonderful, they obey an irreducible representation of the C2V point group. It turns out we weren't quite so lucky when we put these orbitals further away from the center. So when they were centered around atom A and atom B. So neither of these are members of an irreducible representation. And it turns out one of our first clues is the fact that they can transform into each other when I do a C2 rotation or a reflection across the sigma v axis. So if I do a C2 rotation, they flip positions and signs, and reflection across the mirror plane just has them flipping positions. So this is going to be slightly problematic for me because I need to try and figure out a way to make these guys irreducible representations of my symmetry operations. So one of the things that we can hopefully do, but we aren't always lucky enough to do, because sometimes I do have to describe my system as a 2 by 2 matrix. And we'll find a way to describe irreducible representations which don't simplify any further a little bit later. But for now, we are actually quite lucky, as it is entirely possible to diagonalize each of these four matrices, which means, turns out, eigenvalues and eigenvectors comes into favor, but once again. And it happens with our good friends linear combinations. So it turns out that I can construct PA and PB orbitals out of some linear combination of my irreducible representations. So in order to solve this, we would do an eigenvector eigenvalue problem. And it turns out that the irreducible representations that can describe this combination of orbitals are going to be P1 and P2, where P1 is a symmetric combination of A and B, and P2 is an anti-symmetric combination of A and B. And hopefully this looks a little bit familiar from our atomic and molecular orbital sections, but in case it doesn't, visually what this looks like is P1 is going to have 50% of the orbitals on A and 50% of the orbital density on B, and they're both going to be pointed the same direction. And for P2, they'll be pointed in opposite directions. And now what we can essentially do is either use our eigen values that we got from a matrix manipulation, or if, for example, I give you these orbitals, we see how each one of these orbitals actually will transform under each of my matrix operations. And so, go figure, if I apply the identity matrix to both of these, they will stay put. If I apply my C2 rotation, then again, I apologize, I should have an extra negative value. Or actually, yeah, so sorry, if I apply my C2 rotation, my first value, first matrix, the negative will become positive and the positive will become negative as these densities switch. But my P2, the positive stays positive and my negative stays negative. So we get a value of -1 for P1 and a value of 1 for P2. Now let's try our mirror planes. So my first mirror plane is going to cut through the plane of the molecule, or sorry, bisecting the plane of the molecule. So what ends up happening here is that for my P1 orbital, positive becomes positive, negative becomes negative. So we get a value of 1. And for this orbital, for P2, positive becomes negative, negative becomes positive. So I get a value of -1. And then I have a mirror plane that bisects the molecule. So again, along my YZ plane. And when I do this, for both orbitals, negative becomes positive, positive becomes negative in both cases. So both of these get a -1 value. And now what you should notice is that I can describe each one of these orbitals by a single value along the diagonal for each of these operations. So congratulations, these new linear combinations do indeed form irreducible representations of our starting C2V point group. So what it practically means for us is going to be this idea that if I'm going to continue describing the behavior of my atomic orbitals in sulfur dioxide, I really should treat these orbitals as my basis set. So looking a little bit less at how this p orbital interacts as part of the molecule and how this p orbital interacts as part of the molecule, but more how this linear combination of atomic orbitals reacts to form the greater MO. So we've changed essentially what building blocks we use to build part of the molecular orbital, which, as you can imagine, can become a very handy tool in pre-solving a lot of relationships when I start looking at things like Huckel theory or more advanced modeling techniques. So this is one of the reasons why people, especially before the age of modern computing, often liked using atomic orbitals as a way to pre-solve a lot of matrix elements and predict molecular orbital structure. It's a very handy tool to use by essentially hand. But what this also allows us to do is I can now assign irreducible representations for each of these elements. So, for example, my uh, P1 orbital has values of 1, -1, 1, -1. And my P2 orbital has values of 1, 1, -1, -1. And so we can now assign irreducible representations to each of our uh, five orbitals. And so one of the things you should notice is I have 5 orbitals, but 4 irreducible representations, which means somebody shares. So specifically in this case, it means that 2 of our sets of orbitals specifically are px and our px and our p1 orbitals have the same symmetry because they're part of the same irreducible representation. And then each of our 3 other orbitals, py, pz, and p2, all are part of their own irreducible representations. Now, it will turn out later on that this will become a very important feature in trying to predict bond formation in between these orbitals, as symmetry will be a large driving feature of who can make bonds and who can't. However, so far we've been just mostly playing with a simple symmetry group, C2V. It turns out that this becomes a little bit more complicated when I move to symmetry groups that include more symmetry operations, as we have to bring in a couple more features. So next time, we'll start bringing in some ideas that happen when we move to C3V. Till then, take care and stay healthy.